Hi, good morning. Today we are going to start next session. Now this is about section 5.1 classification of spectrum. Last class we have started our fourth sem we have started new chapter spectrum Fredholm theory of compact operators. Now just to recall what we have discussed in our last class. There is no need to write all these things in your note. Okay. So, what do you mean by a regular point? Let A from x to x be a bounded operator. Okay, bounded operator. A complex number lambda belongs to C is called a regular point of A if and only if the inverse operator A minus lambda I inverse, okay, from x to x exists and is a bounded operator. Listen carefully, each term is very important and the definition you must remember each definition. Okay, so a from x to x be a bounded operator. Lambda is called a regular point of a if and only if the inverse operator exists, a minus lambda inverse exists, and it is a bounded operator. Clear? If lambda is not a regular point, we call it as a spectrum point. Okay, and the set of all spectrum points is called spectrum of A and it is denoted by sigma of A. Okay, it is denoted by sigma of A. Okay, so what is sigma of A? Sigma of A is the spectrum of A and it consists of set of all points that are not regular. Okay, hope it is clear. Also, we have proved sigma of A is a closed set, and for every lambda belongs to C with lambda mod lambda greater than norm of A, then it is a regular point of the operator A. Okay. So also we have discussed one theorem in our last session, Banach open map theorem. Let x and y be Banach spaces, and let A from x to y be a bounded linear operator which is one to one and onto. It's not, it is one to one and onto. Then A inverse from y to x is bounded. Xy must be Banach space. A is a bounded linear operator which is both 1 1 and onto. Then A inverse is also bounded. Okay. So today our section is actually classification of spectrum. So we have three type of spectrum point and first one is point spectrum and the second one is continuous spectrum and the last one is residual spectrum. Okay, so there are three types of spectrum point. First one point spectrum, second one continuous spectrum, and the last one residual spectrum. Okay, so what do you mean by a point spectrum? A point spectrum, and its notation is sigma p of A is the set of all eigenvalues of the operator A. Okay, set of all eigenvalues of the operator A. Now what do you mean by an eigenvalue? That is lambda belongs to sigma PA. Sigma PA means point spectrum. Point spectrum is set of all eigenvalues. So lambda belongs to sigma PA if and only if lambda is an eigenvalue means already you know the definition, there exists an x not equal to 0 such that Ax equal to lambda x. So the collection of all these eigenvalues is called point spectrum. Clear? So lambda is an eigenvalue and x is an eigenvector of A corresponding to the eigenvalue lambda. That is, lambda is an eigenvalue and x is an eigenvector of A corresponding to the eigenvalue lambda. Clear? Now, what is actually this is eigenvector x such that ax equal to lambda x implies set of all x such that ax minus lambda x equal to 0, set of all x such that a minus lambda x equal to 0. So, there exists a non-zero x such that ax equal to lambda x means this set is not equal to 0. That means kernel of a minus lambda. What is kernel of a minus lambda? This is kernel of a minus lambda. So kernel of a minus lambda is not equal to 0. So set of all x such x not equal to 0 such that ax equal to lambda x implies kernel of a minus lambda is not equal to 0. Okay. So in our case, if lambda is a point spectrum, if lambda is in point spectrum, then clearly kernel of a minus lambda I is not equal to 0. Once again, you must note if lambda belongs to sigma p of A, then lambda is an eigenvalue and kernel of A minus lambda I is not equal to 0. Clear? Now, clearly kernel of A minus lambda is a subspace of X. And the dimension of kernel of A minus lambda is called multiplicity of the eigenvalue lambda. Multiplicity of the eigenvalue lambda is the dimension of kernel of A minus lambda I. Suppose now here we got kernel of A minus lambda is not equal to 0. Suppose kernel of A minus lambda is equal to 0. What happened? This kernel of A minus lambda equal to 0 means A minus lambda I from x to x is both 1 1. Okay. So A minus lambda I from x to image of A minus lambda is a 1 1 onto map. So this map is 1 to 1 and onto. That means image of A minus lambda is equal to, that is if image of A minus lambda is equal to x, by open mapping theorem A minus lambda I inverse is bounded. Okay, that means lambda is a regular point. What is the definition of a regular point? Inverse image is also bounded. So image of A minus lambda equal to x implies A minus lambda inverse is bounded by open mapping theorem. We will move to open mapping theorem. Let x and y be Banach spaces. A from x to y is a bounded linear map which is 1 1 and 1 2. That is image of A is y. Then inverse operator is bounded. That is same here. Okay. So this map is from x to x. X is a Banach space and this map is 1 1 and on to, if image of A minus lambda equal to x implies this is bounded, that means lambda is a regular point. So if lambda not belongs to sigma p of A but lambda belongs to sigma of A, then image of A minus lambda is not equal to x. Why? Image of A minus lambda I equal to x implies lambda is a regular point. So image of A minus lambda is not, if lambda belongs to sigma of A, then image of A minus lambda I must be not equal to x. So what we get? If lambda belongs to sigma, if lambda not belongs to sigma p, lambda not belongs to sigma, what is the meaning of that? Lambda not belongs to sigma p. Lambda belongs to sigma p implies kernel of A minus I is not equal to 0. So if lambda not belongs to sigma pa means kernel of A minus lambda is equal to 0. That we have assumed here. So kernel of A minus lambda equal to 0 means clearly lambda not belongs to sigma p of A. And finally what we get? If image of A minus lambda is equal to x, then lambda is a regular point. So lambda is a spectral point only if image of A minus lambda is not equal to x. So this is the condition. So if lambda is not belongs to sigma a, but lambda belongs to sigma a, then image of a minus lambda is not equal to x. Okay, you must remember all these things. No need to by heart. Okay, so now next we are going to prove one lemma that is very easy. Let a from x to y be any bounded operator, and let lambda I from I varies from 1 to n be a distinct eigenvalues of a. Let xi not equal to 0 and axi equal to lambda I xi. Then xi I varies from 1 to n are linearly independent. Okay, that is eigenvectors of different eigenvalues are linearly independent. So assume that xi I varies from 1 to n are linearly dependent. Now what is the meaning of that? There exist non-zero scalars. Sorry, here there exist scalars. Actually, there exist scalars alpha 1, alpha 2, etc. Alpha n not all zero such that alpha 1 x1 plus etc. plus alpha n xn equal to 0. So here some alpha is not equal to 0 and we are taking alpha 1 is not equal to 0. Okay. So alpha 1 x1 plus sigma 2 time 2 to n alpha x equal to 0. We rewriting this equation as like this, and lambda alpha 1 not equal to 0. Now take any polynomial or in a polynomial p of lambda such that p of lambda 1 is equal to 1 and p of lambda equal to 0 for I greater than or equal to 2. Here we are assuming polynomial as p of x, p of lambda. That means polynomial in lambda. If lambda replaced by lambda 1, then p of lambda 1 must be 1. If lambda replaced by lambda 2, then p of lambda 2 must be equal to 0. Does there exist such a polynomial? Yes, this is one of such polynomial. If you take p of x equal to, or you can take p of lambda, x minus lambda 2, etc. What about p of lambda 2? Here lambda 2 minus lambda 2, this equal to 0. P of lambda 3, 0, etc. P of lambda n equal to 0. But what happens when x equal to lambda 1? This is lambda 1 minus lambda 2, lambda 1 minus lambda 3, etc. So cancel each other and we will get 1. So such a polynomial there is no need to write things given in square bracket. This is only for understanding the concept. Okay, so now p of a into xi. What is p of a? P of lambda is a polynomial. So you can write, for example, p of lambda you can write as some lambda square plus 2 lambda. Now what is p of a? P of a, you replace lambda by matrix a square plus 2a. So this is a matrix and operator. So what is p of a into xi? P of a into xi you can write as p of a xi. How? This a is a linear operator. Therefore p of a into xi. This of xi you can write as p of axi. Okay. So what is axi? Axi is lambda I xi by our assumption. And this you can write as p of lambda I xi. So p of a xi equal to p of lambda I xi. Xi's are non-zero. Therefore, clearly p of lambda is an eigenvalue of p of a. Okay. So now apply p of a to equation 2. What we get? Here from this we get p of a xi equal to p of a xi equal to p of lambda I xi. Okay. So apply p of a to equation 2. What is equation 2? Here you are applying p of a. So here alpha 1 into p of a x1 plus etc. sigma 2 and alpha into p of a xi. So alpha 1 into p of a x1 plus etc. But p of a x1 is same as p of lambda 1 x1. Here also p of lambda I xi. But all these terms 0 because p of lambda 2, lambda 3, etc. are 0. And here p of lambda 1 is 1, and from this we get alpha 1 x1 equals 0. As the set we are assumed xi is not equal to 0, therefore x1 not equal to 0. This implies lambda 1 alpha 1 equal to 0. Therefore, which is a contradiction because we are assumed lambda 1 not equal to 0. Okay. Similarly, in the case of if you take alpha 2, repeat the procedure and finally we get all other alpha is equal to 0. That means our assumption is wrong. That means that xi are linearly independent. Okay. So moving to our next spectrum, next definition, continuous spectrum notation is sigma Ca. What is a continuous spectrum? The continuous spectrum sigma Ca is defined as follows. Lambda belongs to sigma Ca if and only if lambda belongs to sigma of A minus sigma P of A. And image of A minus lambda I is dense in X. What is the definition? Lambda belongs to sigma Ca if and only if lambda belongs to sigma A minus sigma Pa. What is the meaning of that? Lambda must be a spectrum point, but it is not in point spectrum. Okay, that means what is the meaning of that? Kernel of A minus lambda I is lambda I must be equal to 0. So also image of A minus lambda is dense in X. Lambda not belongs to sigma Pa means uh, kernel of A minus lambda equal to 0 and image of A minus lambda I is dense in X. We have one result. Image of A minus lambda I equal to X implies lambda is a regular point. So for getting lambda is a spectrum point, we must have image of A minus lambda is not equal to X. Clearly, image of A minus lambda is a subset of X. So it may be dense or it is not dense. If lambda belongs to sigma Ca, then image of A minus lambda is dense in X. Okay. So must not lambda belongs to sigma Ca if and only if lambda belongs to sigma A minus sigma P. Also image of lambda A minus lambda I is dense in X. Okay. So moving to one example. Let A from L201 to L201 defined by Ax of t equal to Txt. You have to find sigma A, sigma Pa, sigma C. What is the definition? L201. What about L201? What about the norm in L201? If some x of t is in L201, what is the norm? Norm of x is equal to integral 0 to 1 modulus of x of t whole square all raised to 1 by 2 dt. So this is actually square integrable function. Now we have to find sigma A, sigma Pa and sigma Ca. So Axt is defined as t into x of t. So let lambda belongs to sigma Pa. Lambda belongs to sigma Pa means lambda is in point spectrum. That means lambda is an eigenvalue. That means there exists x not equal to 0 such that Ax equal to lambda x. Now Ax equal to lambda x means Ax of t equal to lambda x of t. That is Tx of t equal to lambda x of t. That is you can take lambda here t minus lambda I x of t equal to 0. And this is true for every t belongs to 0. So if lambda belongs to sigma p of a, then t minus lambda into x of t must be equal to 0 for every t belongs to 0, 1. What about this way? This value is equal to 0 for every t belongs to 0, 1 implies x of t must be equal to 0. Okay. So if lambda not equal, in the case of lambda not equal to t, this is 0 only if x of t equal to 0. And this result is true for every t belongs to 0. Therefore, this happens only if x equal to 0. So that means Ax equal to lambda x implies x equal to 0. So there does not exist an x such that x not equal to 0 and Ax equal to lambda x. That means sigma p of a equal to empty set. Now what? We have to find sigma Cas and sigma A. So for finding sigma A, so our next aim is finding sigma of A. Okay, sigma of A. Sigma of A means we have to check whether A minus lambda I invertible or etc. For which lambda. Okay. So suppose lambda naught belongs to 0, 1. So A minus lambda into x of t equal to A x of t minus lambda x of t, and that's equal to t minus lambda into x of t minus lambda into x of t, as lambda naught belongs to 0, 1 and t belongs to 0, 1, t minus lambda is never be equal to 0. Okay, so a minus lambda, if we can define a minus lambda is inverse as 1 by t minus lambda into x of t, because t minus lambda never be 0 if lambda not belongs to 0, 1. Therefore a minus lambda is invertible, and also it is bounded. Why? X of t is in L201 and it is also bounded. Okay, so integrable function, therefore it is bounded. Therefore a minus lambda is inverse is also a bounded linear operator, which is implies lambda is a regular point, that implies lambda not belongs to sigma I. Therefore if lambda not belongs to set 0, 1, sorry, closed interval 0, 1, then lambda not belongs to sigma I. Clear? Suppose lambda belongs to 0, 1, then a minus lambda into x of t equal to, I'm just skipping all other steps, and we can write like this. Okay, so as lambda belongs to 0, 1, this is 0 for some t. Okay, t is also belongs to 0, 1. Okay, so a minus lambda I is not invertible, because a minus lambda is inverse, the possible term for a minus lambda is inverse is 1 by t minus lambda, but 1 by, we can't define 1 by t minus lambda because it may be 0 at some point in closed interval 0, 1. Therefore a minus lambda is not invertible. This implies lambda is a spectrum point. This is not invertible means lambda is not a regular point. That implies lambda is a spectrum point. That means lambda belongs to sigma A. Thus we get sigma A equal to set 0, 1 and sigma A minus sigma P A equal to set 0, 1 minus set empty set, which is equal to set 0, 1. Now what about A minus lambda I? A minus lambda I is dense in L201 because it is a square integrable function x of t and continuous function. These are clearly continuous functions. Therefore they are clearly integrable, and therefore clearly they are dense in L201. Okay, so sigma C of A equal to closed interval 0, 1. Now moving to last, residual spectrum. What is sigma R of A? Is actually sigma of A minus union of sigma P of A and sigma C of A. That means those spectrum points that are not point in point spectrum and that are not in continuous spectrum is called residual spectrum. That means if lambda belongs to sigma R of A, then kernel of A, lambda not belongs to sigma P of A. That is, lambda is not an eigenvalue. That means kernel of A minus lambda I must be equal to 0. And lambda not belongs to sigma CA, because lambda not belongs to sigma CA means image of A minus lambda I closure is not equal to x. That means image of A minus lambda is not dense in x. Okay, so I'm giving one problem as sample. Consider the shift operator AEI equal to EI plus 1 on L2. Just go through the what is the definition of shift operator. From this, how we get a general definition for shift operator. We have already discussed this operator in our third semester. Then find sigma A, sigma CA and sigma RA. That means residual spectrum. We are just, there is one note. From this moment onwards, we will write lambda I star for lambda conjugate I. Okay, this notation you must remember. Lambda I star we can, sorry, lambda conjugate I we can write as lambda I star. Also, if lambda belongs to sigma PA and lambda conjugate not belongs to sigma PA star, then lambda conjugate belongs to sigma R A star. This result we will discuss later. Okay, just remember this result. Lambda belongs to sigma PA and lambda conjugate not belongs to sigma P A star, then lambda conjugate must belongs to sigma r A star. This is actually point spectrum, and lambda conjugate not belongs to point spectrum of A star, then lambda conjugate must belongs to point spectrum, residual spectrum of A star. Okay, hope everything is clear. That's all for today's class.